Okay, 7.2, the dot product. So the learning goal for this lesson is to determine the dot product between two vectors and determine the angle between those vectors. We're going to start with something called the unit vector in the Cartesian plane. And we're going to define two vectors labeled I and j, and specifically using these letters I and j, as unit vectors, where the tails of those vectors are at the origin and the heads of those vectors are at 1, 0, and 0, 1, respectively. Okay, and so those vectors, if I draw them on the Cartesian plane, look like this. So here's my vector I, so along the x-axis, and here's the vector j along the y-axis. Oops. Okay, and I can use these two vectors to represent any other vector on the Cartesian plane. Okay, they're called unit vectors because they represent the smallest possible unit, not counting decimals, but just let's just say 1 unit big. And I'm going to represent, in this example here, this vector from O to P, which is -6 and 5, in terms of I and j. So if I were to draw O to P, I'm going to -6 along the x-axis and 5 along the y-axis. So point P would be right there. And I can just draw that vector connected to the origin and the arrowhead at point P. Now the question becomes, how many of these vector i's and how many of these vector j's do I need to create the equivalent vector from O to P? So I can start constructing. If I took vector I and I pointed it to the left, I would have negative I. Okay, and then if I repeated that negative I several times here, 6 times, I can reach the bottom leg of my triangle. And then if I took vector j and I added it on 1, 2, 3, 4, 5 times, I would have the vectors I need to get the vector O to P. So O to P can composed of 6 vector i's going to the left, or I can say -6i, and 5 of vector j, so 5j. Okay, so I can write this as OP equals -5i plus, sorry, -6i plus 5j. Okay, so these two equivalent expressions for vectors are the same. So I can express a vector using in a component form, algebraic, -6 and 5 with square brackets, or I could use unit vectors to express the same thing, -6i plus 5j. Okay, so to express any vector in terms of I and j, just think of I being the x component and j being the y component. So whatever x component and y component I read off this form, I can just use those numbers to express them in terms of unit vectors. So -2 and 0 would be -2 and I plus 0j. Okay, but sometimes when you say 0j or 0 of any unit vector, we can just ignore it or not include it and just say -2i. Okay, similarly for 0 and 3, if there's no x component, I'm just going to represent this as 3j. Okay, and for 3 and 2, I can write this as 3i plus 2j. Okay, so we're always doing it in order, x component first, y component next. And so I is the x component unit vector and j is the y component unit vector. And I can go in reverse as well. If I'm given them in unit vector form, I can express this in my square brackets. So 3 i's and 2 j's means my vector is just 3, 2. If I have 4j as the vector here, four of the y component unit vectors, then that's going to be 0 for the x and 4 for the y, so 0, 4. And the last one here, -7i plus 3j would be -7 and 3. Okay, so I want you to pause the video and try questions on the right side. Okay, hopefully you've had a chance to try the questions on the right side. The answers are as follows. So we're going to have negative 1i plus 6j. Then we're going to have, for the next one, 2i minus 7j. And then for the third one, we're going to just have minus 8j. And expressing the unit vectors in the form a comma b, we're going to have here square bracket negative 9 and 0. And for the second one, we're going to have negative 2 and 5. Okay, let's move on to what we are going to do in this lesson, the dot product. So we've learned so far how to multiply a scalar and a vector back in section 6.3. And the result of multiplying a scalar and a vector was another vector. Here we're going to do a different kind of multiplication called the dot product. And when we define the dot product to be as follows, so we have going to have the two vectors we're going to multiply here, a and b. We're going to have a dot between them to represent that multiplication. And that's my dot product. And that's going to be equal to the magnitude of a times the magnitude of b times the cosine of the angle theta, where theta is the angle between a and b. Okay, when a and b are arranged tail to tail. Now notice in this formula, all three parts of the right side, magnitude of A, magnitude of B times cosine theta, are scalar values. Magnitudes are scalars, the cosine of theta is a scalar. So the resulting product is a scalar. Okay, unlike the previous multiplication we did in 6.3, which was a vector as a product, this one's going to be a scalar. And we're going to look at another type of multiplication called a cross product later on, which is different, and that product will be a vector. But in this case, this one we're focusing on producing the scalar product. Okay, so let's look at an example how to use this formula to calculate the dot product. So we're going to calculate the dot product between these two vectors. I have a vector A and then its magnitude is given, and a vector B and its magnitude is given, and the angle between them is 120 degrees. So applying the formula, the dot product between A and B as follows. So we have vector A dot vector B equals the magnitude of A times the magnitude of B times the cosine of the angle between them, 120. And so that's going to be 120 times 65 times the cosine of 120. If you have a calculator handy, take out your calculators, do the calculation, make sure you get the same answer that I'm about to put on the screen here. And so that answer is going to be minus 3,900. So you can get negative values, okay? Pause the video for a moment, try the next question. Okay, hopefully you had a chance to try the next question. And so here we go, A dot B. Make sure you properly write the vector notation, equals, so here we have 145 times 230 times the cosine of the angle between them, cosine of 17. And so that result is 31,892 if I round that, or 93 if I round that to the nearest whole number, okay? And so the dot product can be positive as well. Now, if you're not given a diagram, you could be given a question where it's just, hey, here are the values. Calculate the dot product for each pair of vectors. You have the vector u and v, not a and b this time, but u and v, and the angle is 47 degrees. So the same idea, you take the two vectors, you're finding the dot product, and so you take their magnitudes, 7 and 12, you multiply them, and you multiply that with the cosine of the angle between those two vectors. So 7 times 12 times the cosine of 47, which is equal to 57.3 degrees. And we're gonna, sorry, not degrees, 57.3. And that is just going to be rounded to the nearest tenth. And that's as simple as that. Just take the formula and multiply, substitute and multiply. Okay, try the next one. Pause the video and try it. Okay, hopefully you had a chance. It's just, again, going over the idea that not all vectors have to be A and B. Here's when it says S and T. So the dot product between these two is going to be 520 times 745 times the cosine of 135 degrees. Okay, and this one will be If we have these big numbers here we're multiplying times cosine 135, and that's going to result in a very large negative number, minus or negative 273,933, rounded to nearest whole number. Okay, so that is just a dot product. I want you to take a few moments, pause the video again, and try these 3 questions. And I want you to investigate what's happening here with these vectors. They're all the same vectors with the same magnitudes, just the angles are all different. So try and see tell me what you get when you do these questions. Pause the video now. Okay, hopefully you've had a chance to get the answers here. So remember, we have A dot B equals magnitude of A times the magnitude of B times the cosine of the angle between them. So for the first one, for A, we're going to have 4 times 6 times cosine of 70, and so that is 8.2. Okay, for the next one, we're going to have 4 times 6 times cosine of 90. Well, guess what cosine of 90 is? That's 0. So everything is multiplied by 0. So that's going to give you a 0. And then the third one, we're going to have 4 times 6 times a cosine of 135 degrees. And so that's 4 times 6 times cosine of 135. And that's going to be negative 16.97. Okay, so we have these different results, and I want you to pay attention to the angles. So we have 70 degrees, 90 degrees, and 135 degrees. And you're going to find that for every time you put 90 degrees, no matter what the magnitudes are, your dot product is 0. What's special about the 90-degree angle? Well, that means there are 2 vectors, tail to tail, are perpendicular to each other, right? So you could have vector A here and vector B here. These 2 vectors are perpendicular. And so having the dot product equal to 0 will actually turn out to be very useful in the future problem solving that we do with vectors in this chapter. So that's a very important observation. Any 2 vectors where theta equals 90 degrees, the dot product is 0, okay? Or the reverse, if we said if the dot product of something is 0, then you can be assured that the 2 vectors that make that dot product are perpendicular, okay? What about the other 2? When we have an angle that's less than 90 degrees, so for any acute angle, angle theta, then we have the dot product A dot B is going to be greater than 0, positive. Okay, so you can see that the positive value there of 8.2. That's because of the cosine of an angle between 0 and 90 is going to be positive. And for an obtuse angle, where the angle is greater than 90, cosine of that angle will be negative, right? So the dot product would then be less than 0, negative. Okay, and the magnitudes are always going to remain positive. Okay, so that is the first part, algebraic or the geometric dot product. Just looking at the angles between the 2 vectors and having their magnitudes. The next part is we're going to look at the algebraic dot product. Okay, so when calculating the algebraic dot product, we're going to look at another formula. So let's say we had vector A, and let's say the components of vector A are A1 and A2. Okay, and then we had another vector B, and their components are B1 and B2. Okay, and so remember, these are x and y components, right? So the A1 is the x component, A2 is the y component, B1 is the x component of B, and B2 is the y component of B. So if I'm going to calculate the dot product algebraically, so A dot B will equal, and this is the formula. So we're going to look at A1, x component of the first vector, and x component of the second vector. So multiply those two together, A1, B1. And then to add to that, we're going to multiply the y components, A2 and B2. Okay, and this formula represents the dot product if we are working with algebraic vectors. Okay, so we can get the dot product straight away. Because when you're given these vectors, you're not given the magnitude straight away. You could find the magnitude, or you're not given the angle between the two vectors. So we need a different formula to calculate the dot product. And this is it. This is the algebraic dot product. Okay, so now I'll make one note that if you are interested in where does this formula come from, there's a derivation of it. So it's the derivation of the algebraic dot product or Cartesian dot product. So the derivation or the proof, let's say derivation of this formula can be found on page 373 of your textbook. Okay, so have a look at page 373, and you can find the derivation of the dot product. Now, you're not going to be expected to derive this, but you do have to know the formula. Okay, so here's the formula as presented, and we're going to be using it in some examples. So looking at the next page, here we are. We're going to calculate the dot product between each set of vectors. So here's the first set, 5 and 8, and -2 and 1. So if I'm interested in finding the dot product of A and B, I'm just going to take the x components, multiply them, 5 times -2. And so those are my x components. Okay, and then we're going to add them to the product of the y components, 8 times 1. Okay, so always make sure you do them in the correct order. So x components, then y components. You don't want to be, sometimes the mistakes that happen are students will multiply these two components together and then these two components together, then add them. So that would not be the correct way to go. Okay, so x components first, then y components. And so the next components are 5 times 2, which is -10, plus 8 times 1, which is 8. And then -10 plus 8 is -2. So you can see here that the result is a scalar, which is what we expected from the dot product. It is negative, so that means theta is greater than 90 degrees. Okay, so that's another clue thing that we could clue in here. But yeah, that's what we expected, a scalar product. Now, if I wanted to find the angle between these two vectors, then I'm going to have to go back to the previous geometric formula, right? So let's remember the geometric formula contains angle theta. So let's write that formula down. A dot B equals magnitude of A times the magnitude of B times the cosine of theta. If I rearrange this for theta, I can express this as cosine theta equals A dot B divided by the magnitude of A times the magnitude of B. Okay, so I could find theta. I could find the angle between the two vectors by knowing what the dot product is. So I have something to substitute up there, and the magnitudes of each vector, A and B. Well, I can find the magnitudes of each vector, and I have the dot product already from the algebraic formula. Okay, what about the magnitudes of each vector? How do I find those? Well, let's take A, for example. Vector A, if we just follow the components, says, well, I'm just going to go 5 along the x and 8 along the y, and that will give me my vector A. Okay, so the legs of my triangle are 5 and 8. So think about Pythagorean theorem. I can use a Pythagorean theorem to find that a hypotenuse, that magnitude of A. So the magnitude of A, let's do the Pythagorean theorem. So magnitude of A squared is just going to be 5 squared plus 8 squared, right? So 5 squared is 25, 8 squared is 64. So together that makes 89. So 80, oops, let's erase that. 89. And so if I wanted to find the magnitude of A, I just take the square root of 89, right? Because the magnitude of A squared is 89, so the square root would be the magnitude of A. And similarly, I can find the magnitude of B, well, B squared, by taking the components of B and squaring them. So -2 squared plus 1 squared, which is 4 plus 1, which is 5. And so the magnitude of B, I'm a little bit running out of room here, so magnitude of B is the square root of 5. Okay. So you take that, put that into your formula. Let's make some room here. Cosine of theta equals A dot B, which we establish is -2, divided by the magnitude of A, which we established is root 89, and the magnitude of B, which is root 5. And so we have square root of 89 times the square root of 5. And if you recall how to find theta, you have to use the inverse. So theta equals the inverse cosine of all that, -2 over root 89 root 5. Okay. And take a moment, put it into your calculator, see if you can calculate it. Make sure you properly use brackets, right? So, it's -2 on the top and root 89 and root 5 are multiplied together on the bottom. Okay, so you have to do that correctly. And if you compare your answer with the answer I'm going to put here on the screen in just a moment, square root of 5, oops. We should arrive at 95 degrees. So theta equals 95 degrees, which is what we expected because the dot product is negative. So the angle is greater than 90. Okay. So yeah, 90 or 95.4 or 44 if you want to be more specific. So this is just a rounded number. Okay. So there you have it. I'm going to do another example. In fact, maybe you can pause the video and try the question on the right. Okay. All right, so hopefully you had a chance to try it. Here we go. I'm going to do this one here. The dot product. So the dot product between C and D is going to be, again, multiplying the x components, -1 and 3, plus the product of the y components, 8 times -3, which is equal to -3 minus 24, which is -27. So there's our dot product. If I wanted the angle, I could say cosine of theta equals C dot D divided by the magnitude of C times the magnitude of D. So again, I got that from the rearranging of the dot product formula. And instead of A and B, I'm just using C and D. So where I have the dot product on top, I can replace that with -27. And on the bottom for C and D, I'm going to have to apply the Pythagorean formulas once more. So Pythagorean formulas for C, I will say the magnitude of C is equal to the square root of -1 squared plus 8 squared. So those are the legs of the triangle for vector C. And that's going to equal 1 plus 64, which is 65, so square root of 65. And for vector D, the magnitude of vector D is going to be the square root. Again, applying Pythagorean theorem is going to be the square root of 3 squared plus -3 squared, which is equal to 9 plus 9, which is 18, the square root of 18. So these are my magnitude values. They're going to go right into the formula, square root of 65 and the square root of 18. And theta would then be the inverse cosine of all of that, -27 over square root of 65, square root of 18. Okay. And so if I put that into the formula, put that into the calculator rather, -27 divided by square root of 65, square root of 18. And that is 142 degrees. And again, as we expected, the dot product is negative, so the angle is going to be greater than 90 degrees. Okay, let's do an example where the vectors given are unit vectors. So here I have vector L, which is 2i and minus 3j. So as in algebraic form or Cartesian form, I'm just going to write, let's do my L's like this. I'm going to change the thickness of my pen. Actually, that might help. Okay, so L is going to be 2 for the x component and minus 3 for the y component. And vector M is going to be minus 9 for the x component and 4 for the y component. Right, so I just read those. How many i's, how many j's? The i's are the x component, j's are the y component. And so the dot product, L dot M, is going to be the multiplication of the x component, so 2 for the L and negative 9 for the M, plus the product of the y components, minus 3 times 4. And that equals minus 18 plus minus 12, which is minus 30. Okay, and so then the angle between them, cosine theta, is just going to be L dot M divided by the magnitude of L times the magnitude of M. And substituting our values here, so we have minus 30 on top. And then we go, okay, what is the magnitude of L? What is the magnitude of M? I got to plug in those values. So I got to figure out those values. So the magnitude of L is going to be Pythagorean theorem, L squared equals the sum of the squares of its components. So 2 squared plus minus 3 squared, which is 4 plus 9, which is 13. So the magnitude of L is equal to the square root of 13. Okay. So again, one more time, we're talking about a vector L whose x component is 2, y component is minus 3, right? Like that. And so the vector itself is vector L. This is the hypotenuse of the right angle triangle that we create from its components. Okay. And then vector M, the magnitude of vector M, squared equals the sum of the square of its components, and the components are negative 9 and 4, so negative 9 squared plus 4 squared, which is 9 times 9 is 81, plus 16 is 97, and so the magnitude of M is going to be the square root of 97. So there we have it. We have the two magnitudes that we need. We leave the, I'm gonna, as I said, I didn't mention this earlier, but I'm just gonna leave them as exact form. You never want to really turn these into decimals as you're going through, because then you lose information as you go through. So leave them in exact form. And so here theta is going to be equal to cosine inverse of minus 30 over root 13 root 97. And that's equal to, take out your calculator, do the calculation, make sure you get the same result as I'm about to present here. So divided by, let's see, square root of 13 and square root of 97. Oops. And there we go. Close the bracket, and we get 147.6 degrees. And as we expected again, the dot product was negative, so our angle is greater than 90 degrees. All right. Okay. I'm going to move on to the next part. Key concepts. Just to rehash the key concepts, we have the dot product once more in geometric form and in algebraic form. Let's talk about some properties. Okay, so when you're doing properties, make sure you do these things correctly, right? So think about bed mass first. You got to do your brackets first, right? A dot B plus C. So whenever you're adding vectors algebraically, remember how to do them. You have to add their components, right? So I'm going to do B plus C first. Okay. And so B plus C is going to be 2 plus 4. So add the x components. So I see the x components here are 2 and 4. And then the y components 5 and negative 1. So 2 plus 4, comma 5 minus 1. and that is going to be 6 and 4. So there's B plus C. Now, if I'm doing A dot B plus C, so now I'm going to take vector A, which is 1 and negative 2, and dot it with B plus C, which we just calculated to be 6 and 4. Okay. And so when you're doing the algebraic or Cartesian dot product, you have to multiply their components. So it's going to be the x components first, 1 and 6, plus the product of the y components, negative 2 and 4. And there's your, and the final result is going to be 6 minus 8, which is negative 2. Okay, so there's your answer. It is a scalar result. That's important to note because B plus C produces a vector, but A is a vector dotted with a vector produces a scalar. All right, so vector dot a vector equals scalar. Okay, so that's important to keep in mind. So why did I do it this way? If you thought, okay, what could you have done A dot, well, the brackets sort of help you. Okay, we're going to go do an example where that might be tricky. So let's look at the next one. So next one's reverse. A plus B is in brackets. We're going to do those brackets first and then dot it with C. So A plus B equals, let's add those two vectors first. So we have 1 and negative 2 and 2 and 5. So 1 and negative 2 plus 2 and 5. Okay, so when we add these two vectors, we're going to add their x components together. So 1 plus 2, and then the y components, negative 2 plus 5. And so the result is 3 and 3. Then we're going to take that and dot it with C, right? So A plus B dotted with C is going to be 3 and 3 dot. So A plus B we already established is 3 and 3, and we're going to dot it with C, and C is 4 and negative 1. So dotted with 4 and negative 1. And so remember, we got to multiply the x components, so 3 times 4, and add that to the product of the y components, 3 times negative 1. And altogether, that's 12 plus a negative 3, which is 9. Okay. So as you can see, not quite the same order, the specific order counts. Negative 2 and 9 are different scalar results. And that comes from just the order in which we do these operations. All right, so try the next one yourself. So we have A plus B, you have to add those two together, and A plus C, add those two together. The results are vectors for each of those, and then you have a vector dotted with a vector, right? And then that final result will be a scalar. Okay, I'll leave that for an exercise for you to look at. I'm gonna just go on to the next page. A couple of application and thinking examples here. So here's an application problem. Laura pushes a crate 25 meters with 100 Newton force at an angle which is 10 degrees from the floor. How much work will she do? So in physics, work turns out to be a dot product. Because if you've studied physics and you studied the concept of work, you might recall that work is just the magnitude of the force times the magnitude of the displacement, maybe use the letter S instead of D, times the cosine of the angle between the two vectors. And that's what is a dot product. So work is just a dot product between the force acting on the object with its displacement. So if I have Laura pushing a crate 25 meters with 100 Newton force, so I'm going to just draw a crate, and we're pushing this 25 meters along the floor with a force of 100 newtons at an angle of 10 degrees. Okay, so here's the first time we're actually going to put two different vectors with two different units in the same diagram. And because the product is just a scalar, that's okay, right? It's not like we're going to do we're adding vectors here and they have to be the same units. Here we're doing a dot product, and we can do the dot product of different vectors that have different units. So here we're going to look at work just being the magnitude of the force, 100 newtons, times the magnitude of the displacement, 25, times the cosine of the angle between the two vectors, 10 degrees. right? And then it's simple calculation at this point, 100 times 25 times cosine of 10 degrees. 2,462, and we go say Newton meters, or maybe it's a joule if you're familiar with that one. Okay, and all that says is, yeah, if I pull this crate with a force of 100 newtons, using the rope, yes, you can imagine, yeah, so crate, what's happening here, here's a person pulling the crate with a rope, okay, and that creates a tension force, and that rope is at 10 degrees to the direction of its displacement, okay? So there it is, right? So that is the work done to move that crate 25 meters with that force. Okay, thinking example, the typical kind of find the value of k, right? So how do I find the value of k so that these two vectors u and v are perpendicular? Okay, remember back in the beginning of the lesson, we looked at the investigation. Perpendicular means 90 degrees, right? So if two vectors are 90 degrees, that means their dot product must be 0. So to be perpendicular, u dotted with v must be 0. Okay, that's the key. You have to just, if you know that they're equal to 0, then you can solve this problem, right? So u dot v, using the algebraic formula, says multiply the x components, 5 times 9, add it to the product of the y components, k times 3, and we know that dot product is 0, right? So 0 is on the left side. On the right side, I have 9 times 5, which is 45, plus 3k. Solve. This is an equation where you solve for k. Okay, so if I solve for k, I will have minus 45 over 3, which is equal to, that's my k value, so k is going to equal to negative 15. So a value of negative 15 will make these two vectors perpendicular. U will be perpendicular to v. Okay, so therefore vector u is equal to 5 and negative 15. Okay, try the last one, and that's it. Okay, well, that's the end of the lesson.